All right, so we're here with our honor stat students looking at number 2 from the homework on chapter 15. And this is a problem that asks us to make a tree diagram. So I don't actually mind where you make the tree diagram. If you want to make it in part A or part B, it's up to you. I'm going to make it in part A, but it doesn't matter. Wherever you want to make it, just write small. Okay? So let's start the tree. All right. What is the likelihood that her first flight leaves on time? 0.15. So I'm going to write on time. 0.15. All right. So if there's a 15% chance her flight is on time, what's the likelihood that her first flight is not on time or delayed? 85. Very good. 1 minus that. So I'm going to put delayed for 0.85. Okay. If her flight is on time, what is the likelihood her luggage makes it to the connecting flight in Chicago? All right, so you got to do another branch here. Ready? So another branch there and another one here. And this is luggage makes it. All right? It's hard to read there. Luggage makes it, or whatever you want to use. Luggage, yay! Luggage, exclamation point. It made it. Okay? What's that likelihood? 0.95. So what's the likelihood her luggage doesn't make it? That's going to be 0.05. Okay? What about for the delayed flight? The delayed flight, what's the likelihood the luggage makes it? 0.65. And what about for it doesn't make it? Okay, any questions on the tree? Sorry, it's so hard to read. Who's got a question on the tree? Which one? There's a lot up there. 0.65 is luggage. Yay, luggage. It made it. I'm holding my luggage. You can write bag. Sounds good. And then no bags. Okay, now, whenever you're working with a tree diagram, tree diagram, to go across the tree, you're going to be thinking multiplication. Okay? So watch this. The probability that her flight is on time and her luggage makes it is going to be what? So flight is on time and the luggage makes it. It's 0.15 times 0.95. Saul and Edgar, can you get calculators for everybody? Please? Somebody's got a calculator. I'm going to go all the way. Can you not round? Because one thing you guys want to be doing, especially when you get to college, is don't round until the very end. And we're not anywhere near the end. Okay? So don't round to the very end. Just being helpful. Who still needs one? Your ref? Just ref. Wake up! Okay, so David, 0.15 times 0.95?
0.1425.
Okay, everybody good with that? Now I'm going to fill out the rest of the tree diagram, which is the probability of on time and no bags. I like that. I'm going to use no bags, David. Okay, probability of delayed and luggage. And then probability of delayed and no bags. Okay, so I'm going to go back to on time and no bags. If I follow the tree, That's 0.15 times 0.05. Then delayed and luggage is 0.85 times 0.65. And finally, 0.85, 0.35. Yes, Catherine.
That's a tree.
That's a tree. It's called a tree. Tree diagram.
So like, is there a certain way you have to make it, or you just put them randomly?
Well, I didn't randomly put them.
No, I mean like the line.
Yeah, I would say that I didn't do a great job making the tree. Okay, I'm so sorry the diagram isn't very good. It's my bad.
Oh.
I would have probably written a little bit bigger so I had more room for my branches. Really, the main thing when you're making a tree is you start with 2 branches, and then each one extends with more branches. And this scenario only had flight, on time or not, bags there or not. But there could be more after that, right? Did they make their dinner reservation? Now you've got even more branches. Okay? Okay, all right, let's see. Who's got on time and no bags? Liam, you got on time and no bags? Okay, let's see. Bianca, do you have delayed and luggage? 0.5525? And then let's go with Laura, delayed and no bags? Okay. Now here is one of those moments that I'm not sure your brain has seen yet. We did all that work to find all these different probabilities. And if you were to take each of these 4 numbers and add them together, you get 1. So these are the only likelihoods in these events of happening. Okay? Now, if you add all these up and you don't get 1, you've got a problem. You've got a problem.
So it's always, so no matter what's going to be one, unless you messed up with someone.
Mm-hmm. Okay.
Or there's another factor that we didn't.
Got one. You're right. Right. This is real life. Then you're missing something. All right. But if it's a problem, it's engineered to add to 1. Yes, Daisy? Could have been a good question. All right. Now, I'm actually going to answer letter B first. All right. I'm going to answer letter B, and then I'll do a letter A. It says, what is the probability that her luggage arrives in Denver with her? Well, guys, there's only 4 scenarios here for this problem. All right? Either her first flight is on time and her bags make it. Her first flight's on time, no bags. Her first flight's delayed, she got the bags. Her first flight delayed and no bags. Those are the 4 options. In all of these 4 options, which of these 4 does she get her bags?
2.
First one? And the third one. So all I'm going to do in part B is I'm going to add the probability that her flight is on time and bags plus the probability that it's delayed and bags. So that's going to be 0.1425 plus 0.5525. All right, what's that equal to? What is it?
6,950.
So 0.695? Okay. So in a sentence, if I was writing this as a sentence, that she has about a 70% chance of getting her bags in this travel. That doesn't seem very high. Right? I mean, seriously, gotta be United, right? Oof. Or Delta, don't get me started. Okay. Let's do A. All right? Or let me actually pause. Is everybody okay with B before I move on? So, you okay with B? No, if you're not, what's wrong? What don't you understand? Do you understand how to get all of these probabilities in the tree?
Oh, yeah.
Okay. Or you understand why I chose the first one and the third one? I chose the first one and the third one because the problem asked, she got her bags. All right, what's the probability that she got her luggage in Denver? So in this scenario and this scenario, she gets her bags. So I added those two together. Doesn't need to be an okay if it's not. Okay, great. All right. Now, part A. Are the first flight leaving on time and luggage making the connection independent events? Now, I'm going to go back to what we had said in the chapter 14 quiz. Independent events, that means the likelihood of one happening is unaffected by the other one also happening. Okay? So the way I do this mathematically, I'm going to do it under here. All right, this is for part A. The way I'm going to do this is I'm going to pick one of these events. And I'm going to pick the probability that her first flight is on time. And this is actually given in the problem. In the problem, what's the likelihood that her first flight, is on time? 0.15. Okay? Now here's what it means if they're independent events. All right? Here's what it means. That this probability of her first flight being on time stays the same if I tell you that her bags made it. Okay? So here's how I'm going to write that. The probability that her flight is on time given that her bags made it. That she has her bags. Okay? Yeah, right? You're good. This is what I told you on Friday. If they're independent events, Travis, you have the probability of an event. Call it A. So if it's independent of event B, then the probability of event A happening, given that B has happened, should be the same number. The probability of event A. Like B should be the same. Mathematically, that's what it means to have independent events. The line, what does the line mean? Given. I'm telling you, she got her bags. She's standing in Denver with her bags.
What are you going to do with those?
That's exactly what I'm going to do right now. All right. Now, the formula, yes. No, I got to do the math. Right? I got to prove it. We haven't done any math yet. I'm sorry, Jarvis? It's not a real question? Okay. It is. It's part A. Now, for the conditional probability, this is how it works. I'll put it up here if you want the formula. It's the probability of B in the denominator, and in the numerator, it's A and B. And this is actually one of the formulas I will give you. It's rare, I know. It's a free, I mean, you still got to know it, right? You still got to figure out how to do it. But ultimately, I'm going to give you this formula. All right? So let's see if your brain can do this. What is my event A in this problem? On time, okay? What is my event B, my given? That she got bags. Okay, so in the denominator, I'm going to put the probability she got her bags. And oh my goodness, what did we just find out in part B?
She has a 0.6, 0.7%.
0.695 chance that she's going to get what? Her bags. Oh, look at that. That's my denominator. Now, what's going to be the numerator? The numerator is going to be the probability of on time and bags. We don't need to. We already got it. What's the probability that it's on time and she gets her bags? 0.1425. So that's going to be the numerator. So now, here we go. If I do this math and it's not 0.15, then they're not independent. What did you get, Charlie?
Oh, 2050.
So is that what you got? 2050? So 0.205?
Can we just put like beforehand, like we have to go through all this, but like common sense instead. Just
Common sense. Hit me with the common sense.
That's like,
Yeah, logically speaking,
Yeah,
the plane leaves on time.
and we already saw that.
There's no way that she can. that means that they have.
Because they give a different percentage on bags and no bags.
The bags are being shipped through FedEx, they're riding on the plane with her. So if her plane is late, then the bags are late as well.
Sorry, I was thinking of the FedEx plane.
These two numbers are different anyways, and like.
Here's the thing. Hold on. Right. Dave, we've been over this, right? We've been over that, the whole noises and stuff. That was actually what it was, right? You need to fight the impulse. It's not okay. Okay. Now, what they're trying to get at is, I understand, if you tell me a flight is on time, it makes sense that it's more likely your bags are going to get there. I agree with you. But you guys are trying to like say, in the future, she's got her bags. We're talking about proving this mathematically. Yes, I know. That's how we have to prove it mathematically. All right, there's a difference between, it's common sense, and someone says, show me the proof. It's common sense I didn't murder that man. I was at my house. Where's the proof? Show me the security surveillance footage that shows me at my house. Security surveillance footage, there it is. Surveillance footage that shows you at your house, right? Those are different things. You need the proof. There it is mathematically. So, now let me try to summarize it for you. So it's a 50% chance that her bags get there, that her flight is on time. If I tell you she got her bags, now the likelihood that her flight is on time has gone up to 21%. All right? Which makes sense, because you guys agree that if she got her bags, it's more likely her plane was on time. I agree. I'm just trying to show you that you have to do this mathematically. I'll have a question that asks you to prove it. Okay? Yes, Michelle.
Her flight affects the bags, or the bags affect her flight?
Well, they're not independent, so they both affect each other.
So if her luggage is in there, then she can't go on the plane.
No, that's not what I'm saying, right? She's on the plane. We're saying that her plane leaving on time affects her luggage getting there. If I tell you that she got her luggage, well, that tells me that it's a better chance her flight was on time. You're talking about two different scenarios. One where she's in the plane, like on the plane. One where she's on the ground and already has her bag.
You're talking about the future and the present.
Exactly.
I don't understand how you got 0.69.
Hold on, guys.